Hi dear friends, welcome back. This time it's a special episode in the form of a vlog. Many of you have asked me which telescope to buy, and I always tell you it depends on your budget and what you want to do with it. Do you want to look at planets or do you want to look at galaxies? Are you in the countryside or are you in the city? The conditions are different. Buying a telescope is the same as buying a car. Something that you like, that you can easily take with you when you go to take pictures somewhere else, and so on, your personal choices. I thought the best idea was to discuss my telescope and show you its parts by taking it apart. No, I should mention I can also take the telescope apart, because I bought two gadgets that I really like and that I want to test. The first gadget is a laser collimator for the telescope, because the telescope loses its alignment from time to time and I have to realign it to adjust its mirrors back in place, and usually I do it by eye. But I found this laser collimator which costs about $30, and they say it's much easier to align the laser. Well, since I have the chance to align it, I'll take it apart and show you its components. You'll see, and we'll talk around the telescope. The second thing I bought is this adapter for the mobile phone, because many of us want to take pictures. At first I used an adapter for the video camera, which I use for YouTube. So what was I doing? I would take out the eyepiece from the telescope, the eyepiece is here, I would remove the eyepiece, put on this adapter, and then the camera. But it's pretty hard to work with it. I have to align the camera a bit more awkwardly. Now that I have a good mobile phone, I bought this adapter. And the adapter goes over the eyepiece, so I think it will somehow be easier to take pictures. Okay, what are the main components? I removed the cap. This is the telescope, and this is a finder scope to help you see where you're aiming in the sky. So this thing, it's not that important. What's important is the telescope itself and the area where you put the eyepiece. No, the light comes in here and reaches the back where there's a mirror. This is a Newtonian telescope. Can you see if you can see the mirror back here, right? After that, the light reflects off the mirror, comes back, and in this area in the center, there's a second mirror, the secondary mirror, which is pretty hard to see. Maybe I'll take a simpler picture here, but here is the secondary mirror. And the secondary mirror reflects the light toward the area where the eyepiece is. And we put our eye here, adjust a little, and look at what we want to see. Now show the telescope up close so you can see the secondary mirror. Here is the secondary mirror, okay? Here you can see the back mirror much better. The light enters from the front, reflects off the back mirror, reaches the secondary mirror, which is here, and then the light is reflected and reaches the eyepiece. Okay, let's start disassembling the telescope. I'll start with the primary mirror to check it and clean it a bit. Okay, and now let's take out the mirror. There we go. Ta-dam! This is the reflector mirror. It has some dust on it. I need to clean it. And here, if we look, I think you can see the secondary mirror better. The mirror that's there, which is there and reflects the light and sends it to the eyepiece. So let's clean the primary mirror. I usually use some wet wipes. Okay, I've cleaned it. You don't have to press too hard on the mirror and scrub it too much because you could damage it. I managed to damage the primary mirror of another telescope by trying to scrub it really well like that. At some point the very thin layer came off, because that's not the actual mirror. It has a very thin layer. I think it's silver and it's quite delicate. So if you scrub it really hard, you can damage it. That's why, as you saw, I took a tissue and wiped it very gently. I let the tissue glide over the surface of the glass a few times. And I don't want to insist too much because it really can get damaged, and it's the most important element. That's why, by the way, to keep dust from getting in, I always try to put the lid on top. I check to see if the secondary mirror has dust, but it doesn't, so I'm not going to take it apart. It's harder to put it back, so I won't wipe it. I only wiped the primary mirror. Okay, now I'm going to put the primary mirror back and try to align the telescope. Now that I have the primary mirror, let's discuss how this telescope works and understand it. So a telescope this is a Newtonian telescope because it's based on Newton's principle. This Newtonian telescope has a reflecting mirror. This is called the primary mirror, as I mentioned, a secondary mirror, and an eyepiece. The most important elements are this primary mirror and the eyepieces that are mounted where we look through. I've now mounted an eyepiece there. People are usually interested in a telescope's magnifying power, which has a simple formula. It is given by the focal length of the primary mirror, meaning if this mirror receives light from the sun, it focuses all the sunlight into one point. The distance from the mirror to that point is the focal length. Well, the focal length of this mirror is 750 millimeters. I found it in the technical specifications. However, essentially you expect the image of the sun to be focused roughly where the eyepiece is. So from here to here is about 750 millimeters. That's the focal length. On the other hand, each lens also has its own focal length. Because if I take this lens and put it in the sunlight, you'll see that the light coming from the sun forms a point. Well, the distance between the lens and that point is the focal length of the lens. This lens, for example, has a focal length of 6 millimeters. Usually it's written on it, as I have another eyepiece here, focal length of 10 millimeters, but you can't see it anymore because it's been erased. And this eyepiece, which is the nicest one, is my favorite, it has a focal length of 20 millimeters. Well, in general, the smaller the focal length of the lens, the more it magnifies. Well, this eyepiece has 20 millimeters, so basically it's not that good at magnifying, but on the other hand, it has a large area here, making it easy to look through. It has a wide field of view, so you can see a lot. Now back to the magnifying power. So people are generally interested in how much the telescope magnifies, and that's calculated simply. You divide the focal length of the telescope, in this case 750 millimeters, by the focal length of the lens, which in this case is 5 millimeters, 750, divided by 5 gives us 150. So this telescope at best magnifies 150 times. There's another trick that some people do, and that I also did. Namely, I bought myself a Barlow lens, which is a special lens. You attach it to the eyepiece. Here's the Barlow lens and the eyepiece. You put it together like this. So the lens is placed in, the eyepiece is placed in the Barlow lens, and then it's mounted in this area. Well, and this Barlow lens, which is added in between, magnifies extra by 2 times. It says here it magnifies by 2 times. It's a very special lens. And so if I use the Barlow lens, this eyepiece, plus this telescope, the mirror, I'll increase the magnification from 150 as it was before to 300. And 300 times is the maximum magnification power of this telescope. In practice, I have to say it's useless. It's useless. Why? Because I live in the city, and when I go outside, if I try to see something at 300 times magnification, I won't be able to see anything because of atmospheric turbulence, because of light pollution, and so on. In practice, I use a magnification power of 100 times. When buying a telescope, don't focus on its 1,000 times magnification, because you won't be able to use it, especially if you're in the city. Telescopes that magnify 1,000 times must be taken to mountaintops, precisely calibrated, and are very large before they can be used. If you use a telescope that magnifies 1,000 times from your yard, like I do, you're basically getting it for nothing. Maximum useful magnification in a city is usually around 100 to 200. Some experienced amateur astronomers might reach 300 in certain cases, but for me, it's honestly about 100 times. So I don't really use the Barlow lens, I just use this lens with the telescope, but sometimes I do a little trick. I use the Barlow lens with this very good lens, which has a very large mirror, and then I reach a magnification power, let's say 100 times, but I also see that area much better. I combine the two. And the last thing about the Barlow lens is not to get tricked when you buy it. I once bought one for 30 euros, but it wasn't good. This one cost me 100 euros. Speaking of prices, since I'm here, this telescope cost about 250 euros. And I have to say this again, when you buy telescopes, don't buy them from regular stores like grocery stores or whatever, where you see a telescope on sale. No, those telescopes usually aren't good. They have plastic mirrors, finder scopes, and lenses. No, telescopes should always be bought from specialty stores, and there are plenty in Romania. For example, I have worked with the people from Astrovest, but there are other telescope stores in Romania as well. Now I need to reinstall and align the primary mirror, then calibrate the telescope, otherwise its magnifying power is useless. Even if it's 200 or 150 times, it won't matter if it's not calibrated, because you still won't see clearly. Alright, let me put this back in place. I noticed there were some marks left from the wet wipes, and to remove those marks I'm using a wet wipe, but this one is dry. And if I do this, those marks get cleaned off. And I forgot to talk about the magnification power. I forgot to talk about the things we have here. I remembered because I told you about the magnification power, and I told you about the useful magnification power. However, in fact, what you can actually see with a telescope at most is always given, not by the focal length of the primary mirror or the eyepiece, but only by the surface of the primary mirror. The surface of the primary mirror is actually what determines what you can see, because no matter how well you make the rest of the telescope, in the end what you can see is determined by the surface of the primary mirror. Why? Because it receives light. The larger it is, the more light it receives, and it has an intrinsic limitation, which is the diffraction of light. Specifically, the smaller the mirror is, the more pronounced the diffraction effects are. Your vision isn't as good. The larger the mirror is, the smaller the diffraction effects are, and then you can see better. Now, how do you calculate that minimum angle that you can see? Because I have to tell you this again, in astronomy we're interested in the angles under which we see things. We're interested in angular resolution, right? An angular resolution. If you look at the moon, for example, you have to stretch your left hand toward the left side of the moon and your right hand toward the right side of the moon. And the angle between your two hands is the angle under which you see the moon. And if I'm not mistaken, it's about half a degree. That's the angle under which you see the moon. So that's the apparent angle under which you see the moon. Well, the angular resolution of a telescope, so the angular resolution of this telescope is the minimum angle it can see. And that's given by diffraction. And you can see the diffraction formula here. Essentially, this minimum angle is the ratio between the wavelength of light and the diameter of the lens. For my mirror, we can calculate the minimum angle we can see with the telescope using the diffraction formula. So I need to divide the wavelength of the incoming light, say red at around 650 nanometers. I divide by 150 millimeters and I get about 4 microradians. This is the minimum resolution that I can see with this mirror. Whatever I do with the telescope, even magnifying it 1,000,000 times, doesn't matter. I can't see anything smaller than 4 microradians because of diffraction effects. What does 4 microradians mean? Well, Jupiter, for example, appears at an angle dozens of times larger than the resolution of my mirror. So I can see Jupiter with this telescope. But if I calculate for Mars I got, let's see here, about 30 microradians. No, that's right at the limit. So my resolution, at best, if the telescope is calibrated and everything is really good, is 4 microradians, but Mars has 30 microradians. Well, in practice, I can't really see Mars with this telescope. And I'm telling you, from a practical point of view, that I haven't seen the planet Mars. I mean, seeing the disk of the planet Mars, not something else. To photograph Mars's disk, or possibly see its polar ice, you need a much larger mirror than I have. I couldn't see Mars. The Sun's disk, on the other hand, is visible to the naked eye since the Sun is much closer. Suppose the Sun were 1 or even 4 light years away, like the distance to the nearest star. I can't see the Sun's disk, so looking at stars is pointless since they always appear as points. I'll never see the disks of stars. And there's another aspect that I also like when I think about such mirrors. Namely, sir, how much light can they receive? How much can I see? Because pay attention, this is also good to know. Light is made up of particles called photons. Well, normally to see an object, you need many billions of photons to see that image. I can also calculate how many photons are coming. because I divide the light power coming from the sun by the energy of a single photon. The energy of a single photon is given by Planck's formula, as you can see here. The total energy coming from the sun is known. I can calculate how many photons are coming, and I did this calculation for the sun. If the sun were on the other side of the galaxy, so if the sun were somewhere about 100,000 light years away, I wonder how many photons I would still receive here. And the result is I would only receive a few photons. So essentially my telescope can't detect the sun if it's at the other end of the galaxy. Although the light is still present, it's made of photons, and only 2 or 3 actually reach me. And I was sitting and thinking, by the way, about the future of humanity, that actually if we make mirrors that are really, really, really big, we could actually see really, really well. Ideally, we should have a mirror as large as the Earth's diameter. And then we could see, I think like on television, the nearby stars, the planets really well, and so on. But, well, it's very hard to make a mirror as big as the entire surface of the Earth. Now I have to put the mirror back in place to calibrate the telescope. I shouldn't mess with these buttons. I need to adjust the secondary mirror's buttons. Well, if I'm asleep. I need to adjust the secondary mirror's buttons first to make sure it gets centered. Okay, this is the laser calibration device. The laser is on, I put it here, in place of the eyepiece. It sends a laser beam to the secondary mirror, and the secondary mirror sends the light to the primary mirror. I forgot to mention though, the primary mirror, the one in the back, has a black circle in the center. And I have to make sure that the laser light that falls on the secondary mirror, this one here, reaches the primary mirror in the center of the primary mirror. And if I look here, it doesn't reach it. Well, how can I do that? By adjusting the secondary mirror with these knobs here. I adjust it so that the light falls on the primary mirror. Okay, here is the laser. The light from the laser enters the telescope through the eyepiece area, reaches the secondary mirror. The secondary mirror is this one here. And the secondary mirror sends the light to the primary mirror, the one in the back. And I can see it with the naked eye. I don't think you can see how the laser light doesn't fall in the center of the primary mirror. And then I have to adjust it using these buttons here. Okay, now I've aligned the secondary mirror, meaning the laser light is reflected by the secondary mirror to the primary mirror's center. Now, it reflects back and comes here again. But this reflection depends on the alignment of the primary mirror. And we can see that it's not aligned very well because the laser light doesn't return to the center. The primary mirror has 2 types of screws here. With one type I align, and with the other I lock it in place. All right, and that's it. Okay. Time to take some pictures. I hope the evening will be nice so I can take some pictures of the sky.